All right, welcome to the Explainer. Today, we're taking a seriously dense 50-page professional UAV engineering manual and, well, we're bringing it to life as an accessible, step-by-step blueprint. If you've ever looked at a messy pile of wires, carbon fiber, and circuit boards and just wondered, how on earth does this all come together to literally defy gravity, then you are absolutely in the right place. We're going to build a quadcopter from scratch today, and we're anchoring it all on the incredibly foundational KK2.1.5 flight controller. So grab your tools, and let's turn a pile of parts into a flying machine. You know, the core challenge here is actually fascinating. Think about a traditional helicopter with its complex mechanical linkages and swash plates. A quadcopter doesn't have any of that. It's literally just four fixed pitch blades spinning in space. Because of that, the physics of flight here are inherently chaotic. To even get off the ground, let alone stay airborne, a quadcopter has to generate at least twice as much thrust as its own weight. It's this wild intersection of raw physical force and continuous high-speed calculation. So here is our literal blueprint for today. We're going to cover Section 1, Anatomy of a Quadcopter, Section 2, Selecting Components, Section 3, Hardware Assembly, Section 4, Wiring, Section 5, Configuration, and finally, Section 6, First Flight. Okay, let's jump straight into Section 1, Anatomy of a Quadcopter, the physics and the brain. Now, you might be wondering why our source manual focuses so heavily on the KK2.1.5 flight controller, right? I mean, in a world of modern 32-bit controllers, this is a legacy 8-bit AVR baseboard that'll run you under $15. But here's the thing. It is widely considered the absolute best way to learn how drones actually think. Because it strips away all that modern software magic, you're forced to see and understand raw flight control. It's basically the perfect educational platform. And the absolute crucial point here is how fast this little brain thinks. 200 to 400 hertz. That is the sensor loop rate of the KK2.1.5. To put that into perspective, 200 to 400 times every single second, the onboard gyroscopes and accelerometers are calculating the drone's orientation in space, detecting any tiny tilt or drift, and immediately adjusting the speed of the four motors to correct his balance. That rapid-fire loop, that is literally the only thing keeping your drone from falling out of the sky like a rock. Moving right along to Section 2, Selecting your components, gathering the muscle and skeleton. Think of the frame as your drone's skeleton, and the geometry of that frame directly dictates how it's going to fly. You can go tiny with an ultra-lightweight mini frame for zooming around indoors, or you can scale all the way up to a massive heavy-lift 900mm frame for delivering payloads. But for our blueprint today, standard 5-inch racing or freestyle frames, usually right in that 210 to 330mm range, offer the best all-around performance. They give you the agility you want without sacrificing the stability you really need when you're just learning. But let's talk about the muscle and the sheer power you need to actually lift that skeleton. 66 amps. Okay, that is a dramatic number. It represents the maximum current draw of a standard 2200 milliamp hour 30C battery. When you multiply the capacity by that C rating, you get this massive figure. The electrical power surging through these wires is immense, guys. We aren't just plugging in a little toy here. We are routing serious, high amperage current. Which brings us nicely into Section 3, Assembling the Hardware, Precision and Safety. When you're dealing with the kind of power we just talked about, tiny mechanical mistakes don't just cause a little wobble, they lead to catastrophic failures. Take a really close look at this warning from the engineering manual. When you're mounting your motors, if you use a screw that is just 1 single millimeter too long, actually literally just a millimeter, it'll push right past the base plate and dig straight into the copper stator coils in the motor. The second you plug in your battery, dead short circuit, your brand new motor will instantly fry. High stakes right from the very first turn of the screwdriver. Always, always verify your screw depth. Oh, and here's another classic pitfall: propeller orientation. Props aren't just flat pieces of plastic, you know. They have a specific airfoil shape. You've got the thrust face, which has that curve to it, and then the flat face. If you put the propeller on upside down, and trust me, it is incredibly easy to do, it won't push air downward to create lift. Instead, it's just going to sit there, wildly chopping the air, keeping your drone permanently glued to the floor. All right, let's get into Section 4, Wiring and Electronics, the nervous system. So this is where we connect that massive high amperage battery to the muscles and the brain. And there are some very strict rules here. You gotta route your power wires along the arms. You absolutely must keep your delicate little signal wires separated from those heavy power wires by at least 5 millimeters, otherwise you're looking at a nightmare of electromagnetic interference. Plus, every single exposed solder joint needs to be covered in heat shrink. But listen, the absolute most critical takeaway here is the continuity test. Before you ever plug a battery into your newly soldered power distribution board, you have to use a multimeter to ensure there's no connection between the positive and negative pads. Skipping this? Yeah, that's pretty much the fastest way to start a fire on your workbench. With the nervous system completely checked and verified, it's time for Section 5, configuring the KK2.1.5, waking it up. Now here is the KK2.15's absolute killer feature. It has an onboard LCD screen that allows for complete, on-the-fly field tuning with just 4 simple push buttons: up, down, back, and enter. That's it. You don't need to drag a bulky laptop out to the flying field with you. You can literally just check your receiver inputs, verify your stick mapping, and tune your flight characteristics while you're standing right there on the grass. It is a total game changer. And hey, speaking of tuning, let's demystify PID tuning. I know this is often the scariest part for new builders, but let's just think of it like driving a car on a highway. The P stands for proportional. That's your current correction. If you start drifting out of your lane, P is you physically steering the wheel back. The I is integral. It fixes past drift. So if there's a strong crosswind steadily pushing you off course, I basically remembers that continuous error and leans into the wind for you. And D is derivative. It dampens future oscillations. It's the thing that stops you from overcorrecting and swerving wildly back and forth. You just punch these starter values into that little LCD screen, and the brain takes over the rest. But none of those fancy PID calculations mean a thing if the drone doesn't know which way is up. That's why accelerometer calibration is so vital. You place the drone on a perfectly level surface, navigate to the menu, press enter, and, this is key, hold it perfectly still. Our manual gives a massive warning here. If you accidentally bump or move the drone during the first 5 seconds after power-up, you'll introduce a permanent bias offset into the sensors. The drone's going to think tilted is actually flat, and it will drift uncontrollably the absolute second it leaves the ground. All right, we made it to the final stage, Section 6, safe first flight, tension, and liftoff. Okay, hard stop for safety right here. Our manual is incredibly explicit about this, and for good reason. 10-inch carbon fiber or hardened plastic propellers spinning at 10,000 RPM, those are practically flying lawnmowers, guys. They can and absolutely will cause severe lacerations. So during all of your workbench testing, like when you're setting up the receiver, testing motor directions, or configuring the LCD, those propellers must be completely removed from the drone. No exceptions. Only attach them when you are outside in a wide open field, completely ready for liftoff. Once you are outside and safely backed away from the drone, you initiate the safe arming procedure. This is a brilliant built-in safety mechanism, so your drone doesn't just launch itself directly into your face the second you plug in the battery. First, you power on your radio transmitter. You bring that throttle stick all the way down to the minimum. Then and only then do you connect the drone's battery. To actually wake those motors up, you hold the left stick fully down and to the right for 2 seconds. The motors will briefly spin up, the LED on the KK board will turn solid green, and boom, you are live. So, there we have it. We've taken the complex, chaotic physics of multi-rotor flight and broken them down into a totally accessible, step-by-step engineering reality. You've seen the hardware, the software, the wiring, and the critical safety protocols required to actually tame the skies. So here's the real question. You know the physics, you have the blueprint, what are you going to build? Get out there, gather up your parts, and happy flying.